All right, so these notes cover section 1 of chapter 5 in chemistry. And really, we're just going to be talking about the periodic table. Um, we're going to talk about the roles that Mendeleev and Moseley had in developing that periodic table. And we're going to describe a modern periodic table, talk about periodic law, and we'll also talk about how elements in a group, right, are interrelated in terms of atomic number. There's this pattern, this periodicity that ultimately comes down to electron configuration from last chapter. So a lot of things are going to be tied together a little bit. And so a lot of it's review. It shouldn't be a big deal to pick up on this stuff. But this Mendeleev-Moseley periodic law part, just understand that Mendeleev was limited in what he could do at the time that he made his periodic table, right? He used the mass of given elements to arrange them according to mass and properties, and it worked, but it also didn't work, right? And he had a lot of gaps that needed filled in at the time too, because there were a lot of undiscovered elements, and he actually predicted that some of those elements would exist, and he could predict what properties they might have too, right? By the time Moseley came around, it was a little easier to organize this stuff because we actually knew about those subatomic particles. So, excuse me, he used the atomic number and properties to arrange things, but you'd have to know that a proton existed before you could do that, right? So he had a little bit of an advantage there. But when it's all said and done, once you start arranging things according to their atomic number and their properties, that's when you get that periodic law, right? Now, there's a video that I put on Google Classroom that actually talks about a lot of different things, but I would like you to watch that because it would really make a difference, right? Connect some things together. So it talks a little bit more about what Mendeleev did and how we discovered some of those elements and even some that didn't exist naturally, right? So it's just interesting. Go ahead and watch that. But otherwise, periodic law, physical and chemical properties of elements are periodic functions of their atomic numbers. Again, once we knew that protons were involved and that different elements had different numbers of protons, right? And those protons were related ultimately to electrons that those elements might have in their shells. So all of these things that we've talked about before still going to apply, but now we're going to talk about some different patterns and how you can figure out what kind of properties elements would have. Our periodic table, right? We made sure that things with similar properties fall in the same group or column. So if I look at a periodic table, everything in group 17, all of these halogens have very, very similar properties, right? Obviously, noble gases, super similar. They're all very unreactive and stable, right? Group 1 elements like lithium, sodium, potassium, rubidium, cesium, they're all super reactive metals. You can't even find them free in nature because they react so easily with water. So anytime you're looking at the periodic table, anything in a row is anything that's in the same column, those are all going to have very similar properties. Some special groups, again, noble gases are going to be kind of important. And Mendeleev didn't even know that noble gases existed because they were hard to find, right? Considering they don't react with anything, they can exist in the air that you're breathing and you don't even know it, right? They don't do anything. They don't react with anything, so they're just there, right? So noble gases were helpful because, again, we know that they're super stable, but the reason they're super stable is because they have full shells. So that's how we knew when we got to a noble gas, like neon at the end of that period 2, that we needed to start a whole new row because there'd be a whole new shell of electrons to fill, right? And those valence electrons that we're going to talk about in the future, those outermost electrons, the electrons that are in that outermost shell, those are what contribute to properties of elements. So ultimately, every time we hit a noble gas, we'd start all over again, and you'd see those same properties repeating all over again, because bromine has the same number of valence electrons as chlorine. So noble gases just marked the end of a period. And they're at the end of the period because they have a full shell. In order to get more electrons for that next element, we had to create a new shell, and that's why the pattern starts all over again. Again, lanthanides and actinides, we don't have to say much about those at this point because we've already talked about them a lot. Those are those F block elements. And biggest thing is just remember that it's removed and below. It technically belongs as part of the periodic table. If I click on wide, they can go in there where they belong. But it's a lot harder to fit this periodic table on a piece of paper. In fact, it's probably not even on your screen right now fully, based on what I'm recording. So you can understand why we removed those, put them below. They got some weird stuff going on because, you know, a lot of them are synthetic, man-made, right? A lot of them are radioactive. So they have some specific properties to go with them. But again, when it's all said and done, F block is removed and below, and we did that just to save space. Finally, periodicity, right? This goes back to any given group on the periodic table. So once we got all of these things arranged and organized accordingly based off of their properties and their atomic number, we started to notice certain patterns. So in the group that has hydrogen at the top in group 1, we see that atomic numbers 1, 3, 11, 19, 37, 55, and 87 for all those elements in that first column. We started to see this pattern that was repeating over and over again, right? If you look at the difference between 1 and 3, the difference is 2. Difference between 3 and 11 is 8. Between 11 and 19 is also 8. The next difference is actually 18. The next difference is 18 again, and that final difference is going to be a 32. Now, that may not mean much initially, but you've seen those numbers before, right? We know exactly what those numbers mean at this point, right? Why there would be a separation of 2 here versus a separation of 8, right? Because I told you guys that the first shell only holds 2 electrons, right? Because it only has one sublevel, that S sublevel. And S only has one orbital. Each orbital holds 2 electrons, so there's 2 electrons in that first shell, right? Second shell, though, not only has S, but it also has P. And S has 1 orbital, P has 3 orbitals. That's 4 orbitals combined times 2. That gives me my 8, right? This pattern, this periodicity, this is actually where we came up with all that stuff to begin with, right? We didn't know that there was S, P, D, F. We had no idea about orbitals or subshells and you know, electrons and shells of electrons in general. We had to make all that stuff up to match this pattern, right? These were the original numbers. We had to make everything else fit when it's all said and done, right? So when we talked last chapter about how the first shell, right, 1 squared equals 1 times 2 equals 2, there could be a maximum of 2 electrons in that first shell. That's where we get the 2, right? 2 squared equals 4. So there actually could be 8 electrons in that next shell. That's where we get our 8, right? Now the third shell is supposed to hold 18, but we don't see 18 until we get between that row 4 and 5. And we don't see that for a reason because we talked about how 3D is offset. It actually shows up in that 4th energy level, right? It only shows up in terms of energy once you start filling that 4th energy level. So again, the reason it's not just 2, 8, 18, 32 in that order, why you repeat 8 twice and then repeat 18 twice, is because it takes a second before not only that D sublevel, but also that F sublevel, because that's the difference between 18 and 32, right? When I had 4 squared, I could have 16 different orbitals, and each one of those holds 2, and that's going to be my 32 electrons total. So once I get to that 4th energy level, I do have possible F orbitals to fill, but again, not going to fill those until late because they have high energies. So you still follow the off-bow principle. There's that offset. That's why it's not just straight up 1832. But we've seen all these numbers before, and it doesn't matter which column you use, right? I could use the halogens and see that fluorine's 9, chlorine's 17, bromine's 35, 53 for iodine, 85 for acetylene, and then this tennessine that I've never heard of is 117, right? The difference here is going to be 8. This difference is going to be 18, right? Next difference is going to be 18 again. Then I got a 32, and then I got another 32, right? Over here, I only saw 32 once, but I still see the same numbers when it's all said and done, right? And those patterns are reoccurring for a reason, right? Because we have these shells that have subshells that have orbitals, and there's a total number of electrons per period based off of those things, right? But once we get to that noble gas, that shell is full. I have all 1832 electrons that are available to be in that shell, and then I have to go to a new one. So that's all we need for this section.